So now we can move on to the main topic of this video lecture, albeit optimization. This is a process of finding the minimum or a maximum, for that matter, of functions, or now even sets of data, large sets of data, which of course approximate functions in the long run. This is a very well developed branch of applied mathematics, and there are therefore a number of techniques available. There's the so-called non-derivative methods, which include the important Nelder-Mead method, gradient descent methods. We have genetic algorithms, simulated annealing, and linear and nonlinear programming. The process can be summarized by finding the minimum of a vector function subjected to a number of constraints. So we say this is a minimum such that the function, the minimum of an objective function I, and then we have another of what we call fi functions, which are constraint functions, which will be less than a particular vector when n goes from 1 to all the way up to n, big N. It should be strenuously noted that there's certainly no general solution to the problem, and hence a number of methods are used to solve rather specific cases, and will be the main subject now of this video lecture. So I think essentially the easiest way to see these things is the techniques, what we call the non-derivative techniques, such as the Nelder-Mead, is to look at this in 2 dimensions, the so-called downhill simplex. These essentially use triangle analogues, so triangles in 3D. So for instance, a triangle, a simplex in 3D would be the tetrahedra that you've come across probably from meshing in fluid dynamics. And there'll be 4 dimension and 5-dimension and 6-dimension analogues of these, as we'll see. However, obviously we can't draw these, as we can only see things in 3 dimensions. These essentially, as I say, use simplexes, which are triangular analogues to find, by selecting the minimum point and dividing the distances from the minimum to the other 2. 2 in 2D points are shown. So here we're trying to find a minimum, and we would have basically 2 guesses where we think the minimum occurs, and we would strike one halfway between those 2 extremes, and we would compute the value of the function which we're trying to find a minimum of. We can then just turn around and say, okay, right, which one's smaller? So what's closest to the minimum? Well, in this case, it's that one, and that one. So we just choose this one and this one as we move forward. Okay. Well, this one and this one are now minimum. So we'll choose that one and we'll compute. Oh, that's handy. Now I've blown this up so you can see it. That's handy. Only these 2 now. Then I've blown this up again so you can see it again. Only these 2. And eventually you'll find that the algorithm will, an algorithm such as the downward simplex method will eventually find the minimum, probably after quite a lot of iterations. And also it must be said that this is for very simple for this particular function, but for functions with lots of variables, this is very, very cumbersome and extremely slow. So there is the Nelder-Mead minimization technique, and an analogous gradient method called the Powell algorithm use sophisticated methods in which to find these minimum. But that's essentially the idea of what we call the gradientless methods. This is because the gradient which we've just been talking about, the gradient of the function, the gradient vector, is not computed at any point with these algorithms. estimations are used, or very, very educated guesses, as in this example, are used instead. So moving on swiftly to the Nelder-Mead method. This is one of the most important and as is dimensionless, gradientless. More correctly, I should have said gradient-free. And this is one of the most important of the lot. It's called the Nelder-Mead algorithm. It would be applicable to ask you this in a test. What are the main, to describe the main phases of the Nelder-Mead algorithm? Wouldn't ask you to code this up, but maybe ask you to code up the downhill simplex, for instance. This is essentially an improvement to the downhill simplex, and works much better, of course, for 3 dimensions, 4 dimensions, 5 dimensions. But again, we shall use this accordingly to show you how really easy it is to implement within Python, because this is all done in the background. But essentially, you have 3 points. You would sort these out, and then you would choose the 2 lowest, and whenever the highest one is, you would reflect that, because if you reflect it, then it's so for instance, if we reflected on this one, nothing would happen, so we get exactly the same value for 2 dimensions, but that's fine. In 3 dimensions, if you reflect, you'll probably be going downwards. Probably, not always. So we reflect, and then we put W equal to R, and then if R is greater than U, so it's the lowest value, then they use some type of extend, so they try and extend further down, and they keep extending further down that line until it actually becomes greater. So they go on this particular line and keep extending down until it starts to become greater. If it's the opposite, thereafter you can contract. So you look at R and then contract it back. Otherwise, you can shrink the whole. So the Nelder-Mead isn't very important. So you can contract or shrink depending on what's appropriate after they've tried the extension routine. But the whole process is hard coded into Python fantastically. So to actually produce the minimum of this particular, which we've just done, of course, using our downhill simplex to find this, and of course you could use it differentiation from also to find this minimum, because it's only one variable differentiation. Here we simply have we'd set up a lambda which would be x0, x1 and x1. So here we have a 2 variable problem. This one was a 1 variable problem. This is now a 2 variable problem. And x0 and x1 are essentially x and y. So x0 corresponding to x and x1 corresponding to y, because as we said earlier, the optimization process is to minimize a vector function, and the vector function in this case would be x and y, which is corresponding to z. So we would set this up, so this is x squared plus 4x, which is x0, y squared is x1 squared, y is x1, and then x0 times x1 corresponds to xy. And then it's a simple matter of saying minimize, because we've from the SciPy optimize, we've imported the minimize function, so it would be to minimize the function given the bounds. This is the search area, x1 to x. Is there a minimum value within there using the Nelder-Mead algorithm, or alternatively using the parallel algorithm, which is another dimensionless, gradient-free type method. Simple as, and that's how to optimize using Python. So earlier in this lecture we saw that the direction of the gradient vector indicates the greatest slope of the function, and moreover that its magnitude is the value of that greatest slope. So if one would like to find a minimum going in the opposite direction, would be a salient way to try and find the minimum and use an algorithm which to compute that each time, is the basis of the so-called gradient descent methods. The method is highly analogous to the Newton-Raphson routine, which we use to compute the roots of a polynomial, or of roots of nonlinear functions, I should say, where the new value is approximated from the old value multiplied by some constant, and the gradient of evaluated at the old function, and then it's computed over and over again. We'll see how this works out here. So we have a function here which is z y squared minus xy plus 2y plus x squared minus 5x, and we can compute its gradient or its Jacobian. The way in which we do that is we say the grad of z is equal to j, differentiate with respect to x and put that in the I slot, and differentiate with respect to y and put it in the j slot. So we have the function that I want to minimize, the optimization function, which is I've set up here as a lambda in Python, and I'm putting x1 equal to y and x0 equal to x. Usual nomenclature. I mean, in retrospect, we should have possibly called this x1 squared minus x0 x1, which is probably more usual in the language of optimization. But not to confuse matters, I've just mapped x1 equal to y and x0 equal to x in this particular case. I've done this manually, and then I've used the built-in Python system. So this is something for you to, again, play around with. There will be some exercises for us to complete within the workshop sessions, but put simply, I've set up an array, a NumPy array, and I've put the old value initially equal to 1.2 and 2.8, and then I've set up this many iterations, and I've said that x goes from I equals 1 to n plus 1, so 26 iterations, I guess, and then I've said the new value is equal to the old value minus 0.1, this was arbitrarily chosen, times the gradient of x old. And the gradient of x old is actually here, but of course would have to be called before I issue this. It's just I've changed this for space and for aesthetic reasons. So the gradient is simply this. Now we would have minus x1 from here, 2x0 from there, and minus 5, and here we have the gradient of 2x1 minus x0 plus 2. So it is exactly the gradient as you, and hence why we needed to go through this process of reminding you of what the gradient function is and why is that used interchangeably with this idea of the Jacobian. So two methods in which to do it. I've just iterated for 25, and the other one I've done a more sophisticated method where we've set up the first two, the values of x and y. Initially I've put the new equal to 0 times the old, and then thereafter we have put the number of iterations. So while this convergence criteria, which is the L1 convergence criteria, is less than or equal, greater or equal, I should say, to minus 1 times 10 to the 5. So while that number is greater than that value, and of course this minus this will of course give you that result. Then I've said the new value, and this time I've used 0.225 just so you can see the differences between the two on how quick or slowly they can converge. And we have x new, and then I've just applied the formula, equals x old minus grad f. Grad f is another function, of course, which would need to be called before this, just to remind you. And x new, I've just applied the formula, and then I've tried to compute the norm, L1, that's what the NM's for. This is called the error norm, or the norm, the L1 norm, which is the maximum value between the x new and x old, which will give us a single value, of course, even though it's working on vectors. And then I've said put the old equal to the new, and thereafter put n equal to add 1 to n. This is the plus equals business here, and this will tell us the number of iterations. So we'll know n, the number of iterations, but the while loop will finish once it's converged to 4 decimal places. This is where we've got 1 times 10 to the minus 5. An alternative and much more efficient way of computing these for any function whatsoever are the lines below, where here I've used the conjugate variable method and a couple of algorithms, Newton's conjugate variable method, which is a variation on a theme, and the Boyd-Fletcher Golden-Shumarov method. And I've also used a bounded version of that with the least memory constraint version of that also. And each one of those hopefully will give you some very, very similar results when you try those in the, which will be close to the minimum that you can, of course, compute by the methods, analytically by the methods that we developed earlier in this video lecture. There are other methods available, and there's no real reason to go into these in any great detail. I'm simply going to show you how to implement these within Python, and then if you do want to look at other codes such as Maxima, or sorry, not Maxima, MATLAB or Scilab, or indeed ease, then you could possibly look at algorithms that could achieve this for you. One of them is a genetic algorithm, and these are actually imported from a different part of the Python universe, and this is called from genetic algorithms. I'm going to import genetic algorithm as GA. Again, set up the lambda. This is simply the function as before, and this time it's just a simple GA. GA F2, tell that it's a real, give the original array, and then ask it to run the... There is something called Bayesian hopping, which is analogous to simulated annealing. This we would need to set up the optimizer as shown here, and more detail on that from the Skippy optimize Bayesian hopping. These are what's known, these are the other methods included here will find a global minimum rather than local minimums within a specific range. There is linear programming also, though this is a slightly different problem which is available through Skippy optimization, and I guess what we would need to do is set up the linear programming problem, and to do that we need to understand the notion of least squares. So probably one of the most important methods of optimization is this technique in reducing the errors between a assumed fit of the data, assumed function, and data points. So it's almost an inverse way of interpolation. This time we assume that we have a function and we try and fit the data to that function, and we say how well does this function is representative of those data. And thereafter you can differentiate the underlying function should you need to, and also use that underlying function at least as a guess, initial guess for optimization routines as the ones we've just seen. But the technique is used to minimize the error between data and an assumed function. The result is sometimes used to interpolate between points and even extrapolate outside it, as we'll see. And the setup is as follows. We simply say that for any, this is polynomial least squares, but it need not be. It could be other functions in here, but we'll concentrate on polynomial and then look at other functions when we get a more robust routine within the data-driven optimization software such as Python. But basically we have a bunch of x and y coordinates in space. So on this side we can just put y's, and depending on what values we have on the other side, we could, if we assume a linear function, we could say this is 1x, and if so, in here we would have the first value of x, then the 1, then the first value of x, then 1, the second value of x to correspond to y. Or if we assumed a quadratic, this function here was a quadratic, we would have the first value of y, and corresponding to this in this matrix we would have 1 times the first value, and then the first value of x, then the first value of x squared, and if it was a cubic we'd have a cubic. But the idea is we keep the values here like and like. So if there's the first value here, then it's the first values that we put throughout this matrix, and so on. And next to this we would have our unknown quantities, the values we want to solve for in essence the values of the coefficient values. So for instance, if this was a linear problem, which is the one you're probably very familiar with, we would say y is equal to BO plus B1 times X1. And that's what we're trying to solve. And then for every single one of so the model y equals BO plus B1 X1, we could generate an equation for each one. However, we now have an over-constrained problem, and we need to come to see how we can solve this over-constrained problem. That is to say, we've got too many equations. So in this case, in the case of the linear problem, we would have n equations and only 2 unknowns. And for a quadratic problem, we would have 3 equations, so we would have n equations and 3 unknowns, and the unknowns in this case would be BO, B1 and B2. If it was a cubic, then we would have n equations and 4 unknowns, etc. So the problem is, how do we solve this? Well, the first thing to notice is that we do have a matrix form, albeit this is a rectangular matrix rather than a square matrix to what you're used to. We have the vector y, which is a vector of, make no mistake, this is just a vector of the y values. And then we have a matrix A, which we can easily compute. It simply depends on what order we want the polynomial to be, but the easiest one would see A, the first x value, 1, the second x value, 1, the third x value. So it would just simply be 1, 2, 3, whatever the x values are as we move across in the x-axis. So the least squares procedure effectively minimizes the square of the errors. The error is defined as the actual measured value minus the model value, in this case A, the matrix A multiplied by the vector B. We assume here that the errors are column vectors computed from each value of y minus a, the matrix A multiplied by b. As E is a column vector, then the transpose of E times the vector E would render the square of the errors, and what we need to do is differentiate this with respect to the vector B and set the result equal to 0. The following lemmas are of use from linear algebra. We note that A transpose A times B, so at the transpose of a vector multiplied by this vector AB can also be written B transpose A transpose multiplied by A. So essentially these can swap round as long as we transpose A. So the B can come over here, the A comes to here, they swap round, and this becomes transpose of A. Another result that is required is the quadratic form. So a quadratic form is if we differentiate the quadratic form A transpose A times A, then we require the result. This can be proven, and I recommend that you look at Introduction to Applied Mathematics by Gilbert Strang, or the complementary materials for this particular proof, where you would find that it is A plus A transpose, and that simply we need to take an A into account from this part and the transpose of A from the other part when we differentiate. Note that if A is symmetric, then the familiar 2A times little a would be, or the vector A would be familiar here, because this essentially is A times A squared. So we differentiated that almost in the normal way. So these two will be used for when we for the derivation to follow. So we need to start off with the error squared, or the transpose of the error vector multiplied by the error vector will give us the error squared. The definition of the error is the model is the recorded value, or the measured value, minus the model, which is AB in both cases, and of course we've transposed this one. When this is transposed, we can simply take the transpose inside the brackets here, so this becomes the transpose of y. However, this becomes reversed because the transpose of a product is equal to the reverse transposed. So we reverse it and take the transposes of each. So this is the B transpose A transpose, which is used actually to prove the initial lemma here. And there we have this just comes down for the ride. So the first thing to notice is y transpose times y, when we multiply this bracket out, is actually no longer a function of b. Then we'd multiply y by this, which is so it'd be y transpose times AB. Then we multiply this, which is B transpose A transpose times y, and then we have B transpose A times A B. And we're being careful here to multiply in the right order, as we know that order is important when multiplying matrices together. So now we're in a position to use the fact that, first of all, this first term is not a function of b, so will just disappear on differentiation, so we'll ignore this term. We now need to do something with this term, and we see that what we would like is that it in the form y A transpose, so we need to do something with this. So we'll reverse these round. This becomes B transpose, this becomes Y, so long as this becomes A transpose. So essentially this term here is identically equal to this term, so we've got two of them. So we have 2B A transpose Y plus, and then this is just for the ride, and I've included parentheses here just to indicate that this is actually a matrix And moreover, this matrix is always symmetric, because if we took the transpose of this, well, we'd reverse it and then take its transpose, we would have A would come to the front and then it would be transposed. This one would be retransposed, so you get exactly the same result back. We now differentiate. We need to differentiate this one as we would normally. This is straightforward. This is just a function of b and everything else is constant in this particular expression, so the b simply disappears as it does for nominal differentiation. This one is exactly in this the second lemma form, so we need to but the matrix A now is actually A transpose A, so the idea is you write down the matrix and then you transpose it. So we've said here that this is the matrix, and then we've wrote the matrix again down, A transpose times B, using the second lemma. Now just a little bit of work on this part. We simply reverse and take the transpose, so the A we'd write the A down first and take its transpose and then retranspose A. Well, the transpose retransposed is simply the matrix back. So we have A transpose A, A transpose A. So as promised, if this matrix is symmetric, which in this case it certainly was, then we simply got 2 A transpose A times B, so twice this matrix times B, because it's in the quadratic form and we have a symmetric matrix. So this is lovely. The 2's of course will cancel, because we can divide both sides by 2 as it's just a number, and then finally this hops over to the other side to give us the remarkable result of A transpose A times B, A transpose Y. So we have a form YAB where A is no longer a square matrix. Well, the solution protocol is given by this remarkable result, and it is literally to just try and get the matrix square. And the way in which to get a matrix square, a square matrix from a rectangular matrix, is of course to multiply it by its transpose. The advantage of that also means that it is a symmetric matrix. So we have y is equal to AB, multiply both sides by transpose, and then we've simply got a matrix times A is equal to a vector. So therefore this is indeed in the right form for us to solve by Gaussian elimination. So here we have a concrete example. We want to compute the mechanical properties of a composite material, and we have some discrete data values of the displacement of this composite in millimeters and the force required in which to do it. We know that it's a 40 ply symmetric composite, and its dimensions are 50 by 100 by 5 millimeters in thickness. A compressive test was conducted, and we need to estimate the effective elastic modulus of the material. Note the elastic modulus is defined as the stress over the strain, so we will need to convert these data into stress and strain and stresses accordingly. Once we've found this estimate, we should be able to use it to predict the force applied at the displacements 0.5, 0.3, 4.25 and 6 millimeters respectively. Here we need to note that at 0.5 we're outside the range, so this would be an extrapolation, and 6 is also outside the range, so it would be an extrapolation. So one way in which to do this would be to employ the methods of interpolation and extrapolation that we did before, especially since we've got a force. That said, the underlying physics can be applied here, and the underlying physics is probably linear elasticity, looking at the amount of strain is up to about 3%. So the Python solution is relatively straightforward and can be done in numerous ways, and we'll look at them in turn, but they're basically looking them to get a verification of our results more than anything else, and then using another code for complete verification, more complete verification. So we could enter the data. I've entered it into a NumPy array simply by entering the values into the first and second rows and then transposing it. I've then allowed variables L to be 50, B to be 100, and the thickness to be equal to 5, and then I've stacked the data, restacked the data using the old data, dividing by L to give me a strain, in this case the length, 150 rather, and then I've converted the value of the force into megapascals. That is to say, I've divided by the force in newtons by the area breadth multiplied by the thickness, or divided by the breadth then divided by the thickness, however you want to look at it, to provide the area, so that's force over area, and the value is in newtons per millimetre squared, which is the same as the megapascal. The formula are then applied, but here I need to remember to remind you that we're actually using a new function here in Python. We're going to use the least squares function for solving the underlying equations in the least squared manner, as what we've just derived, just get straight out of the box. And this is in the NumPy linear algebra part. We import least square. So the first simply sets up 1, which is ones, which is the length of the data, and x is the first column of the data, or the 0th column of the data in Python speak. And then we set up a matrix A by simply vertically stacking them and transposing 1 and x, which is great. So we'll stack those one over each other. It needs a tuple. The tuple just needs to be the names of the particular variables. I know that out of VStack we get the result would be a NumPy array, which I can transpose in the normal way by the .t method. And then I've extracted y from the data as the first column, or column 1, which is actually the second column in Python speak, because we've got a 0 order index in the arrays. And then I've said y is the n by new axis, to put that into another axis so it points downwards in the right direction, in which to, and then I've just issued simply list squares A, given the A matrix, and y, and then I said take the first value of that, because it will output a list, and all we want is the 0th value of that. We can plot this. This is relatively straightforward. Epsilon is just a linear space from the maximum of the 0 column data and the maximum column data, and I've used 101 spaces. I've then plotted the data with little default circles, and I've labelled those data. And then below it I've then plotted the epsilon against B0 and B1, because it will give me the list which I require, multiplying that by the epsilon, and I've got a least squares fit of the data, and then I've just simply labelled I've used the plot x label method and y label methods to do the x and y accordingly. And finally I've asked it to plot the legend. So these are the data, and here's the best line fit, which is plotted using these commands. And finally I've said, okay, I want to get a nice little verification of this. So I'm going to use the optimize, but this time I'm going to import the least squares. So I've set up a function, and the function is a lambda function, which is of a, x, y, and x and y. A here is a vector, 1 and 0, minus y, and you'll see why in a moment. And then I've asked for the residual. So the residual for the least squares is equal to the least squares function, which is the function which I'm trying to optimize. I've given it some initial values, minus 300 and 600 in this case. I've then given it arguments. Well, the arguments are x, y, and y1. So they're the arguments which I also need to go into that function. And then finally, hopefully this should give us the result of the least squares algorithm. Or so it will compute this for me directly. And finally, I've said epsilon is again the same as before, and then I've plotted epsilon least squares result. The result of the least squares x1, result of the least squares x2, because the method x will give me the actual results of the least squares. So either method should give us the same result, and hopefully that's something that you can verify nicely within the sessions, within the workshop sessions to come. This can also be done in Maxima, and the commands here are set here. Again, we set up a matrix, and the matrix are of ones and each of the values divided by L. We then set up a secondary matrix, which is a column vector. This is simply y divided by the y values multiplied by 1,000, and then divided by the area b times t. We've assumed that b, t, and l have been previously defined here, and then to find the fit we simply do the A transpose A dot. Remember, the dot in Maxima is the matrix multiplication operation, and then we have transpose A times Y. So it's literally just applying that formula and finding B in that formula. And we plot them in the usual way. This time we need a discrete to flatten the arguments of the matrix and flatten the arguments of Y. So there's a little bit more work to do to understand what's going on there, but essentially you should get the same result, and you can work out exactly what these flatten commands are doing in the particular session or within your own time. Solutions in MATLAB and Scilab are very, very similar. Simply here we've set up the L, B and T values according to the same as we did before. The data are then set up. We now have ones and the data from the first row multiplied by L, and then we've set up a column of Y's, and we've used the / command to compute because underneath the fit there is a if the matrix are not square, then it resorts to solving the problem, an over-constrained problem, using the least squares method by default in both Maxima and MATLAB, so it's worth knowing. Another alternative method would just be, say, the second of the A, which are the data in stress and in strains, and then fitting that with the data in the Y values, doing a single polynomial fit, and these can be plotted in the normal way. So some observations. The constant value from this regression has no physical meaning. So what you'll actually find is that you've got, if you was just to do the regression blindly in this case, you will get a constant value for this. If you extend this down to 0, that's not far to see, you'll see that you'll get a value which will be higher than 0. So this means that at a 0 strain, there's still a stress within the material. Now this may be true, there may be some residual stresses in there, but it doesn't really make any sense for a compressive test when trying to compute the elastic modulus. If such demonstrative evidence is present, then it's always the maths must give way to the physics. So in maxima here, we've used the least squares estimates, which is another function, and we've said, given the data x and y e star, so this is the model, just compute me e. And then we have this object called an MSE, the mean square estimate. It will compute those out, and then I can ask for the least squares estimate, giving me to compute the estimate for E. Such a modification is not possible with polyfit commands. However, it is rather trivial with using the linear algebra developed previously. So if we was to do it with the linear algebra previously, we just require the data, we just require the stresses and the strains. We'd find A as the first lot of the data, B as the second lot of the data, and then we can just apply the formula blindly. These methods will give you values of 43.9 using maxima, 43.3, and if you was to do an analogous method in something like Scilab, I think you get 42.96. So interpolations. Since the whole of the elastic response to the material until failure is known, then better estimates can be obtained from interpolation. So what we could do at this particular moment is we could interpolate, as I said, and the way in which we've done that is use the 1D interpolation. We could do a linear interpolation between the data 0 and 1, and then a quadratic, and of course and perhaps a cubic. We can then put the strains in that we require them out, which is, if you care to calculate these out from previously, these would be 1.2, 2.2 and 3.3 divided by 100, of course, to put them into percentage of strains, and then we could simply plot these values on to see what we would get as far as a linear interpolation, a quadratic determinant, and a cubic interpolation. And you'll see that if this is the estimate of the true estimate, then the interpolation apart from the second interpolation, the other two are in quite some way off what we would expect. You can plot those using the least squares interpolation method, which is shown below. Extrapolation. So any values outside can be estimated using extrapolation. Of course, the closer we are to the range, the better. Using our improved estimates of the modulus, estimate these values. Well, I've computed these out to about 44, as you've seen, so I've made those estimates accordingly, and these are the particular interpolation methods. So these would be the values obtained outside the range at 4, 5 and 6, for instance, and then you'll see you'll get very different values depending on how the data is spread from the interpolation methods. So but it's still worth using the interpolation to see whether you're relatively close, especially if you're close to the data sets, because if you're a million miles away, then there may be something wrong with the underlying least squares.